What if life in the universe didn't wait for the perfect moment to emerge? What if it rushed onto the cosmic stage, appearing in the turbulent dawn of existence itself? Picture this: a universe barely a few 100 million years old, its first stars still flickering to life, its galaxies nothing more than fragile wisps of light. And yet, in that primordial darkness, the impossible might have already happened. The ingredients for life, those delicate chains of chemistry that make up everything we are, could have been stirring far earlier than we ever dared to dream. This isn't just speculation, it's a frontier of science that challenges everything we thought we knew about life's origins. We're used to thinking of Earth as the cradle of biology, a safe harbor where life had billions of years to experiment and evolve. But the universe operates on scales that dwarf our imagination. In the grand cosmic calendar, life on Earth might not even be an early adopter. There could have been entire civilizations that rose and fell before our solar system even existed. The question isn't just when life began, it's how close to the beginning it could have possibly started. So let's rewind time back to when the universe was a blank canvas, still painting its first structures. We'll explore the wild, untamed conditions of the early cosmos where searing radiation, violent supernova, and swirling clouds of raw elements set the stage for something extraordinary. Could life have clung to existence in those extreme environments? What would it have looked like? And if life did emerge that early, what does that mean for our place in the universe today? Buckle up, because we're about to dive into one of the most thrilling mysteries of all: how early the spark of life could have ignited in the darkness. To understand how early life could have appeared, we need to step into that ancient universe, a place so young, so raw, that even stars were a rare spectacle. The Big Bang left behind a simmering soup of hydrogen and helium, but it was missing something crucial: the heavier elements like carbon, oxygen, and nitrogen, the building blocks of life as we know it. These elements couldn't exist, yet they needed the fiery furnaces of the first stars to forge them. And those stars, they weren't like the ones we see today. They were behemoths, hundreds of times more massive than our sun, burning fiercely and dying young in cataclysmic explosions. But here's where things get interesting. When those first stars exploded, they didn't just vanish, they scattered their guts across the cosmos, seeding the universe with the very ingredients life would need. Carbon for structure, oxygen for water, nitrogen for proteins, all of it hurled into space by supernova. And this didn't take billions of years. Some of the earliest stars may have died only a few 100 million years after the Big Bang, meaning the recipe for life was already being written in the universe's infancy. Now imagine those heavy elements drifting into cold, dense clouds of gas, collapsing under their own gravity to form second-generation stars, ones with planets circling them. For the first time, worlds could exist with the right chemistry for life. But could anything survive in such a hostile environment? The early universe was bombarded with radiation, ripped by cosmic shocks, and littered with debris from dying stars. Yet life on Earth has shown us that Extremophiles organisms thriving in boiling vents, frozen tundras, or acidic pools can exist in places we once thought impossible. So why not in the early cosmos? If life can cling to existence in Earth's harshest corners, why not on a primordial planet bathed in the glow of a young, violent star? The universe may have been chaotic, but chaos doesn't mean lifeless. It might just mean life had to be more resilient, more adaptable than anything we've ever seen. And if that's true, then the story of life isn't just an Earth tale. It could be a cosmic epic, one that began before our world was even a speck of dust in the void. Those first stars' population 3 stars weren't just cosmic oddities. They were the universe's alchemists, transforming the primal hydrogen and helium from the Big Bang into something revolutionary. Picture a star so massive it could dwarf our Sun 100 times over, burning with such intensity that its lifespan was a cosmic blink, just a few million years. But in that fleeting existence, something extraordinary happened. Deep in their cores, the crushing pressure and searing heat forced atoms to collide and fuse, creating elements that had never existed before. Carbon, the backbone of organic chemistry; oxygen, vital for water and breathable air; nitrogen, a key ingredient in proteins and DNA. These weren't just elements, they were the universe's first building blocks for complexity. And when these giants died, they didn't fade quietly. Their deaths were titanic explosions, supernovae so powerful they outshone entire galaxies. In those eruptions, the newly forged elements were blasted into the void, scattering across interstellar space like seeds in the wind. This wasn't a slow process. Some of these stars could have died as early as 200 million years after the Big Bang, meaning the universe went from sterile to fertile in what amounts to a cosmic heartbeat. But here's the puzzle: how quickly could these raw materials have come together in the right way? We know life needs more than just the ingredients. It needs them in the right concentrations, in stable environments, with energy sources to drive chemical reactions. The early universe was anything but stable. Radiation from young stars and quasars bombarded every corner. Gas clouds collided violently. Yet amid that chaos, pockets of calm must have existed, regions where heavier elements could clump together, cool, and form the first solid particles of dust and ice. Think of it like a cosmic kitchen. The first stars provided the ingredients, but the recipe for life needed the right conditions to mix them. Some theories suggest that in the dense disks of gas swirling around second-generation stars, these elements could have concentrated rapidly. Water might have formed on dust grains, carbon chains could have linked up in the cold depths of molecular clouds, and ultraviolet light from nearby stars might have provided the energy to trigger more complex chemistry. The timeline is staggering. Within just 500 million years of the Big Bang, a fraction of the universe's current age planets with oceans, atmospheres, and organic molecules could have already existed. That raises a tantalizing possibility. Life might not have needed billions of years to emerge. If the ingredients were present early enough, and if the universe could carve out even temporary safe havens, then the first living organisms might have appeared when the cosmos was still in its wild, adolescent phase. And if that's true, it changes everything. It means life isn't a rare accident that required the perfect, slow simmer of cosmic evolution. Instead, it could be a natural outcome of the universe's chemistry, emerging wherever and whenever the conditions allow. The early universe wasn't a barren wasteland. It might have been a nursery, cradling the first sparks of life in the most unexpected places. The universe was waking up. For millions of years after the Big Bang, space had been a foggy void, filled with neutral hydrogen gas so thick it swallowed light whole. But then something extraordinary happened. The first stars flickered on, their ultraviolet light piercing the darkness like cosmic lighthouses. This was the dawn of the Era of Reionization, a time when the universe transformed from an opaque abyss into the transparent expanse we know today. For nearly 1 billion years, those early stars and galaxies blasted the surrounding gas with so much energy they ripped electrons from hydrogen atoms, ionizing vast regions of space in a slow, relentless wave. And here's where it gets fascinating. This wasn't just a backdrop change for the cosmos. Reionization reshaped everything. The same radiation that cleared the cosmic fog also flooded the universe with lethal levels of ultraviolet light, enough to shred delicate molecules and sterilize unprotected worlds. At first glance, that sounds like a death sentence for early life, but nature has a way of finding loopholes. Just as Earth's ozone layer shields us from the sun's harshest rays, pockets of the early universe might have offered shelter. Dense clouds of gas, the shadows of planets, or even underwater environments where liquid water could absorb and diffuse harmful radiation. Think of it like a storm sweeping across an ancient landscape. Out in the open, nothing survives, but in caves, under thick canopies, or deep beneath the surface, life finds a way to endure. The same could have been true during reionization. Planets orbiting small, dim stars, ones that emitted less ultraviolet light, might have been safe harbors. Or perhaps life didn't need to hide at all. Some extremophiles on Earth thrive in radiation-rich environments, using protective biofilms or rapid DNA repair mechanisms to withstand conditions that would kill most organisms. If life could evolve those tricks here, why not in the early universe? The timing is key. Reionization didn't happen everywhere at once. Some regions of space ionized early, while others remained shrouded in neutral gas for hundreds of millions of years longer. That means there could have been Goldilocks moments when the radiation levels were just low enough for chemistry to take its first tentative steps toward biology. And if life did emerge during this era, it would have had a head start of epic proportions. Imagine civilizations rising under the light of the universe's first stars, their night skies ablaze with young galaxies still forming. But the real surprise, we might already have evidence. The James Webb Space Telescope is peering back to this very epoch, hunting for signs of early galaxies, and possibly even the chemical fingerprints of life. If we find planets with oxygen or methane in their atmospheres from that time, it could mean biology was churning away while the universe itself was still in its adolescence. That wouldn't just rewrite the story of life, it would prove the cosmos was ready for it far sooner than we ever imagined. These first planets weren't like the familiar worlds we see today. Imagine a landscape sculpted by a young, unstable star, its light flickering wildly, its solar winds howling with raw energy. The building blocks were there: silicon for rock, oxygen for water, carbon for organic chains. But everything was amplified, intensified. These worlds would have formed in the turbulent wake of those early supernovae, their surfaces bombarded by leftover debris, their atmospheres seared by ultraviolet radiation from nearby massive stars. Yet even in that chaos, there's reason to think some of these planets could have been havens. Take their orbits, many might have circled small, dim stars called red dwarfs. These stars are cosmic marathon runners, burning so slowly they can last for trillions of years. Even in the early universe, a planet orbiting one could have found stability, nestled in a habitable zone where temperatures allowed liquid water to pool and persist. And water, as we know, is the universal solvent, a stage where chemistry can dance toward biology. But stability isn't just about location. Early planetary surfaces might have been volcanic hellscapes, their crusts thin and fractured from relentless heat. Yet Earth teaches us that extremophiles thrive in hydrothermal vents, where scalding water meets mineral-rich rock. If life here can cling to such places, why not on an ancient world with geothermal vents spewing nutrients into primordial seas? The energy for life wouldn't have to come from sunlight alone. Chemical reactions deep underwater or in subterranean caves could have fueled the first organisms. Then there's time. 500 million years might seem lightning fast for life to emerge, but consider this. On Earth, the leap from simple molecules to single-celled organisms might have taken less than 200 million years once the planet cooled. If the recipe was right, a steady supply of organic material, liquid water, and energy, the same process could have unfolded far earlier in the universe. The real wild card is atmosphere. Early planets might have been shrouded in thick blankets of hydrogen, a gas that traps heat efficiently but offers little protection from cosmic radiation. Yet recent studies suggest hydrogen-rich atmospheres could actually help shield surface life, acting as a buffer against harmful particles. And beneath such an atmosphere, exotic forms of photosynthesis might have evolved, using infrared light instead of visible sunlight to power biological processes. So were these worlds too chaotic? Perhaps not. Chaos creates opportunity, a mixing pot where chance encounters between molecules could spark something new. The early universe wasn't a sterile lab with perfect conditions. It was a workshop, messy and unpredictable, where life might have forged itself in the heat of creation. And if that's true, then the story of life isn't about waiting for the perfect moment. It's about seizing the first one. Earth's extremophiles are like nature's daredevils, organisms that laugh in the face of conditions we once thought were utterly lifeless. Take Deinococcus radiodurans, a bacterium so tough it can survive doses of radiation thousands of times stronger than what would kill a human. Or the Thermococcus species, thriving in boiling hydrothermal vents where temperatures exceed 200 degrees Celsius. These aren't just biological curiosities, they're proof that life doesn't need a gentle, Goldilocks environment to take hold. It just needs a foothold, however precarious. Now, stretch that resilience across the cosmos, back to a time when the universe was a volatile, radiation-soaked playground. Early planets orbiting those first stars wouldn't have been serene oases, they'd have been battlegrounds, with surfaces scorched by ultraviolet flares and skies lit by the constant fireworks of nearby supernova. But extremophiles teach us something crucial. Life doesn't just endure harsh conditions, it adapts to them. If a microbe on Earth can wrap its DNA in protective proteins to withstand radiation, why couldn't an ancient organism on a primordial world evolve similar tricks? Consider the energy problem. On Earth, life doesn't always rely on sunlight. Deep underground, in caves devoid of light, ecosystems thrive on chemosynthesis bacteria converting minerals and gases into energy. On an early planet where the sun might have been a dim, erratic flicker, similar processes could have taken root. Volcanic activity could have provided heat and chemical nutrients, while hydrothermal vents might have served as natural incubators, sheltering fragile biomolecules in their mineral-rich chambers. Then there's the sheer speed of adaptation. Some extremophiles can evolve resistance to lethal conditions in just a few generations. In a universe where environments changed rapidly, where a star's outburst could sterilize a planet's surface overnight, life wouldn't have the luxury of slow, gradual evolution. It would need to be fast, and if Earth's organisms are any indication, that's not just possible, it's practically inevitable. But here's the twist. Early life might not have even needed to resemble Earth's extremophiles. The rules of biochemistry could have been entirely different. On a planet bathed in hydrogen sulfide or ammonia, life might have used exotic solvents instead of water. Genetic material might have been built from silicon chains rather than carbon. The point isn't that early life had to mirror Earth's, it's that the universe is a laboratory with endless experimental setups. So when we ask if life could have existed in the cosmos's violent youth, we're not just asking about survival. We're asking about reinvention. Life might not have been a rare fluke, it could have been a force, erupting wherever chemistry and energy collided in the right way. And if that's true, then the story of life isn't about perfect conditions. It's about creativity, resilience, and the sheer stubbornness of existence itself. Dark matter is the universe's silent architect. While it doesn't glow, absorb, or reflect light, its gravitational pull is the invisible hand that sculpted the cosmos. Picture the early universe a swirling sea of gas and dark matter, the latter acting like a cosmic scaffold, drawing ordinary matter into dense pockets where galaxies and stars could ignite. Without dark matter, the universe might have remained a formless void, its matter too spread out to clump into the structures that make life possible. But here's the twist. Dark matter didn't just shape galaxies, it might have shaped the very environments where life could arise. Think of it like a hidden conductor, orchestrating the dance of galaxies from the shadows. In the earliest epochs, dark matter's gravitational pull accelerated the collapse of gas clouds, compressing them into stars and planets faster than they would have formed otherwise. That speed could have been critical. If planetary systems coalesced earlier, life might have had a head start, a chance to emerge while the universe was still young. And those planetary systems wouldn't have been identical to ours. Dark matter's uneven distribution could have created pockets of extreme density, where planets formed with unusual compositions or orbits. Imagine a world bathed in the faint glow of a dim star, its surface enriched by exotic elements funneled into its orbit by dark matter's unseen tides. But the influence might go even deeper. Some theories propose that dark matter particles could accumulate in the cores of planets, releasing heat as they annihilate one another. On a cold, distant world, that heat might be just enough to maintain subsurface oceans' liquid water in places where sunlight never reaches. We've seen this possibility in our own solar system, where moons like Europa and Enceladus hide oceans beneath their icy shells, warmed by tidal forces. Dark matter could have created similar oases in the ancient universe, offering refuge for life in the most unexpected corners. Then there's the mystery of dark matter's interaction with life itself. While it's notoriously elusive, some scientists speculate that certain forms of dark matter could have subtle effects on chemistry, even influencing the stability of DNA or the behavior of enzymes. It's a wild idea, but not impossible. After all, life on Earth evolved in a universe dominated by dark matter. Who's to say it didn't leave its mark in ways we're only beginning to imagine? The lesson here is profound. Dark matter isn't just a cosmic placeholder, it's a dynamic force that might have nudged the universe toward habitability. By accelerating structure formation, creating exotic environments, or even fueling hidden energy sources, it could have set the stage for life far earlier and in far stranger places than we ever thought possible. And if that's true, then the story of life isn't just about stars and planets. It's about the invisible threads weaving through the cosmos, pulling the universe toward complexity, and perhaps toward life itself. The cosmic microwave background is more than just a relic of the Big Bang. It's a snapshot of the universe's first moments, frozen in time. Imagine stretching this faint afterglow across the entire sky, a tapestry of microwave radiation that holds the secrets of cosmic infancy. Those subtle variations in temperature, those tiny hot and cold spots, they're not random. They're the fingerprints of density fluctuations, the gravitational seeds that would one day grow into galaxies, stars, and planets. But here's what's truly remarkable. Those fluctuations aren't just about structure, they're about timing. By mapping the CMB's patterns with exquisite precision, scientists can reverse engineer the universe's expansion, calculating how quickly matter clumped together in those early epochs. The math is staggering. Some models suggest the first star-forming regions could have collapsed within 200 million years of the Big Bang, meaning planets, real, rocky worlds with the potential for oceans and atmospheres, might have existed while the universe was still in its cosmic diapers. Think of the CMB as a cosmic breadcrumb trail. The hotter spots mark where matter was denser, regions that would later become the gravitational anchors for galaxy clusters. The colder spots, those were the voids, the stretches of space where matter was thinner, slower to coalesce. And nestled within those dense regions, the first protoplanetary disks could have already been spinning, their swirling gas and dust pregnant with the raw materials for life. The implications are profound. If habitable planets formed that early, then life didn't just have a head start, it had a sprinting advantage. While Earth was still a distant dream in the universe's future, other worlds could have been basking in the glow of their young stars, their chemistry already churning toward biology. The CMB doesn't just tell us when this might have happened, it hints at where. By tracing those ancient density variations, astronomers can identify the cosmic neighborhoods most likely to have hosted the universe's first life-friendly environments. And the clues keep coming. Recent studies of the CMB's polarization, the way its light waves are oriented, reveal even finer details about the universe's infancy, like the turbulent motions of primordial gas and the exact timing of reionization. Each new discovery sharpens the picture, turning speculation into testable science. The CMB isn't just a relic. It's a detective whispering secrets about a time when the universe was young, wild, and possibly, just possibly, already alive. Panspermia turns the universe into a grand biological highway, a network where life could have spread from world to world, not just as a rare accident, but as a fundamental feature of cosmic evolution. Imagine a young galaxy, its stars packed closer together than they are today, their planetary systems buzzing with comets and asteroids hurtling through shared space. In such tight quarters, a single microbe-laden rock ejected by a collision or volcanic eruption wouldn't just drift into emptiness. It might find itself tugged by the gravity of a neighboring star, catapulted toward a new home before the organism inside even had time to perish. The math is startling. In today's sparse galactic neighborhoods, the odds of material swapping between star systems are slim. But rewind to the universe's first billion years, when protoplanetary disks were still thick with debris and stellar distances were 10 times shorter. Back then, a microbe frozen in an icy fragment wouldn't need miraculous luck to make the journey just time and the chaotic dynamics of a crowded cosmos. Some simulations suggest that under these conditions, life-bearing debris could have hopped between planets within a single system, or even between stars in as little as a few million years. But survival is the real wild card. Space is a lethal environment. Freezing temperatures, brutal radiation, and the vacuum itself all conspire to sterilize anything daring enough to hitch a ride. Yet Earth's extremophiles have already proven that some organisms can weather these extremes. Certain bacteria, like Bacillus subtilis, have revived after years exposed to space on the exterior of the International Space Station. Others, like the hardy Deinococcus radiodurans, can repair their shredded DNA even after absorbing radiation doses that would liquefy human tissue. If these earthly organisms can endure such trials, why not their ancient cosmic counterparts? And the early universe might have offered unexpected advantages. Less competition meant fewer predators. Younger planets, still geologically active, could have provided hydrothermal vents or subsurface oceans as ready-made incubators for incoming life. Even the chemistry might have been friendlier, fewer toxic heavy elements, more primordial organic molecules floating between stars. Panspermia isn't just about survival, it's about opportunity. A single successful transfer could have turned a sterile galaxy into a fertile one, with life spreading like fire across dry tinder. Here's the twist: we might already have evidence. The Murchison meteorite, a 4.5 billion-year-old relic that landed in Australia, contained amino acids, the building blocks of proteins, with structures unlike anything found on Earth. Were these molecules forged in ancient interstellar clouds, or did they hitch a ride on a rock ejected from some long-dead world? Either way, they prove that the raw materials for life can traverse the cosmos. So if panspermia was possible in the early universe, the implications are staggering. Life might not have needed to start from scratch on every habitable world. It could have been a contagion, leaping from planet to planet while the cosmos was still in its infancy. And if that's true, then the search for life elsewhere isn't just a hunt for independent origins. It's a cosmic ancestry project, tracing the family tree of biology back to a single spark that lit up the darkness before most stars had even finished forming. The Fermi Paradox isn't just a question, it's a cosmic riddle that grows even more puzzling when we consider how early life might have emerged. If the universe was already crafting habitable worlds within its first billion years, why does the night sky feel so silent? Where are the echoes of those ancient civilizations, the megastructures, the signals flickering between the stars? It's as if the cosmos set the stage for life, only for the actors to vanish before the play truly began. One possibility is as sobering as it is simple. Early life might have been too fragile to endure. Picture those first planets bathed in radiation, their atmospheres shredded by solar flares, their surfaces scoured by asteroid impacts. Even if life did spark into existence, the universe's brutality could have snuffed it out before it had a chance to flourish. Imagine a microbe clinging to a hydrothermal vent, only for its entire world to be vaporized by a nearby supernova. The early cosmos was a gauntlet, one that few organisms might have survived long enough to evolve into complexity. But fragility isn't the only answer. Another haunting explanation is that advanced civilizations, if they ever arose, might have self-destructed. We know all too well how quickly technology can outpace wisdom. On Earth, we've teetered on the brink of nuclear war, grappled with climate change, and now wrestle with artificial intelligence's unintended consequences. If a civilization reached our level of advancement in the universe's first few 100 million years, could they have navigated these pitfalls? Or would they, like a candle burning too brightly, have consumed themselves before they could spread beyond their home world? Then there's the eerie possibility that we're looking for the wrong signs. Our searches for extraterrestrial intelligence focus on radio waves and laser pulses, technologies an ancient civilization might have abandoned or never used at all. What if their communication methods were as alien to us as their biology? They might have harnessed neutrinos, gravitational waves, or even quantum entanglement to send messages across the stars, channels we're only beginning to explore. The silence isn't necessarily empty. It might just be speaking a language we don't yet understand. And what if we're the outliers? Life could have arisen countless times in the early universe, each time hitting an evolutionary wall. Perhaps intelligence is rare, perhaps technological advancement is a fluke, or perhaps civilizations tend to turn inward, building virtual paradises or transcending physical form, leaving the material universe behind. The Fermi Paradox forces us to confront not just the cosmos but ourselves. If life is so fleeting, so fragile, or so prone to self-destruction, what does that mean for our own future among the stars? The paradox doesn't just deepen the mystery, it reframes it. The question isn't just when life could have appeared, but why it seems to leave so little trace. The universe's early chapters might be filled with stories of life rising and falling, civilizations blooming and vanishing, all before Earth's sun even ignited. And if that's true, then the silence of the cosmos isn't emptiness. It's an archive waiting for us to learn how to read it. Hydrogen-based life flips the script on everything we assume about biology. On Earth, carbon is the superstar, the element that forms the backbone of proteins, DNA, and every living cell. But in the early universe, hydrogen wasn't just abundant, it was practically the only game in town. Picture a world where oceans aren't made of water but of liquid hydrogen, where atmospheres are so thick with the gas that they trap heat like a cosmic blanket, and where life's chemistry runs on an entirely different set of rules. This isn't just science fiction. Scientists like astrophysicist Avi Loeb have floated the idea that hydrogen-based organisms could exist, not as fragile anomalies, but as robust life forms perfectly adapted to environments we'd consider lethally hostile. Take temperature, for example. Hydrogen becomes liquid at temperatures near absolute zero, meaning these theoretical life forms wouldn't need the gentle warmth of a sun. They might thrive in the frigid outskirts of a primordial solar system, their metabolism slowed to a glacial pace, their cells stabilized by the very cold that would freeze earthly biology solid. And then there's energy. Carbon-based life relies on chemical reactions fueled by oxygen or sunlight, but hydrogen-based organisms could tap into entirely different sources. In the dense, high-pressure atmospheres of gas giants, or even in the freezing depths of interstellar clouds, hydrogen molecules might form complex structures, creating chemical pathways we can't yet imagine. Some researchers speculate that superconducting materials forged in the extreme cold could even play a role, allowing energy to flow with near-perfect efficiency. But the real mind-bender, hydrogen-based life wouldn't just be different, it might be invisible to our current search methods. Our telescopes hunt for biosignatures like oxygen or methane, gases that scream life. To us, but a hydrogen-dominated biosphere might leave no such traces. Its waste products could blend seamlessly into the background of a hydrogen-rich atmosphere, its energy cycles silent to our instruments. We might have already glimpsed such worlds without realizing what we were seeing. The implications are staggering. If life can arise from hydrogen's simplicity, then the universe's earliest epochs, when heavier elements were still rare, might have been teeming with biology we'd struggled to recognize. It's a humbling thought. Our carbon-centric view of life could be just one page in a much stranger cosmic story. And if that's true, then the search for life isn't just about finding another Earth. It's about learning to see the universe through entirely new eyes. Gamma-ray bursts weren't just cosmic fireworks, they were extinction events written in light. Picture the most powerful explosions since the Big Bang erupting without warning, their beams of radiation slicing across galaxies like cosmic scythes. In the early universe, these GRBs were relentless, occurring 10 times more frequently than they do today. A single burst could unleash more energy in seconds than our sun will emit in its entire lifetime, bathing entire star systems in lethal radiation. For any fledgling life clinging to existence in that era, these eruptions weren't just a threat, they were apocalyptic. But here's the twist: destruction isn't always total. Just as nuclear winter theory suggests some life might survive a global catastrophe on Earth, the early universe could have harbored refuges, places where biology ducked the cosmic crossfire. Deep underground, beneath miles of rock and ice, organisms might have been shielded from the worst of the gamma rays. Subsurface oceans, like those suspected on Jupiter's moon Europa, could have served as natural bunkers, with thick layers of water absorbing harmful radiation before it reached delicate ecosystems. Even the atmospheres of gas giants, dense with hydrogen and helium, might have diffused enough radiation to protect floating microbes in their upper layers. The real filter wasn't just survival, it was timing. GRBs tend to be brief, lasting from milliseconds to a few minutes. Any life form that could endure the initial blast might have faced a second challenge, the aftermath. The radiation would have ripped apart atmospheric molecules, creating toxic nitrogen oxides that could blanket a planet for years. blocking sunlight and triggering global cooling. On Earth, we've seen how mass extinctions reshape evolution. In the early universe, GRBs might have acted like a cosmic sieve, allowing only the hardiest organisms, those capable of hibernating for decades or metabolizing unconventional energy sources, to pass through. Yet there's an ironic possibility. GRBs might have accelerated life's complexity. Catastrophic events often force rapid adaptation. If bursts repeatedly sterilized surface environments, life might have been driven to more extreme niches, evolving novel survival strategies. Some theorists even suggest that GRBs could have delivered rare heavy elements to nearby planets, seeding them with materials essential for advanced biochemistry. The same explosions that threatened to erase life might have inadvertently supplied its building blocks. The lesson here isn't just about danger, it's about resilience. If life could endure the universe's most violent tantrums, then its story isn't one of fragile accidents, but of relentless tenacity, and that changes how we search for life today. Instead of only hunting for Earth-like worlds, we might need to consider the survivors' planets orbiting quiet stars in GRB-safe zones, or moons huddled in the protective magnetic fields of gas giants. The cosmos might not be a graveyard of failed biology, but a hidden archive of life that refused to quit. Biosignatures are the universe's hidden fingerprints, tiny chemical whispers that could reveal life existed billions of years before Earth even formed. Imagine a telescope powerful enough to dissect the light from a planet orbiting one of the universe's first stars, spotting the faint spectral signature of oxygen or methane in its atmosphere. These gases don't just linger by chance. On Earth, they're constantly replenished by living organisms. Find them on an ancient world, and you might be staring at the ghost of biology long gone. But biosignatures aren't just about gases. They could be molecular patterns like the left-handed twist of amino acids that dominate Earth's proteins, a quirk thought to betray life's influence. Or they might be unexpected imbalances in elements, like phosphorus levels that defy geological explanation. Even the seasonal ebb and flow of atmospheric chemicals could hint at something stirring beneath the surface. The challenge isn't just detecting these traces, it's distinguishing them from the universe's natural chemical noise. A whiff of oxygen might mean algae-like organisms, or it could be the aftermath of a planet's water molecules ripped apart by ultraviolet light. That's where next-generation tools like the James Webb Space Telescope and the upcoming Habitable Worlds Observatory come in. These instruments won't just snap pictures of distant planets, they'll dissect their atmospheres molecule by molecule, hunting for combinations that shouldn't exist without life's touch. Imagine finding both methane and oxygen in the same atmosphere, gases that normally destroy each other unless something keeps replenishing them, or spotting the telltale haze of organic chemicals drifting above a planet's twilight zone. The real game changer, time travel by proxy. When we peer at galaxies billions of light years away, we're seeing them as they were in the universe's youth. If biosignatures lurk in their ancient starlight, we could effectively witness life's first acts without leaving our cosmic neighborhood. Picture this: a telescope detects the faint infrared glow of chlorophyll, or some alien equivalent, on a world that ceased to exist before our solar system was born. The implications would be staggering. Life wouldn't be a latecomer to the cosmic party. It would have been there from the earliest chapters, threading its way through the chaos of the young universe. Yet the search is fraught with cosmic red herrings, abiotic processes, volcanic eruptions, asteroid impacts, even the chemistry of alien stars can mimic biosignatures under the right conditions. That's why scientists are hunting for technosignatures too, like industrial pollutants or artificial light on exoplanets. If early civilizations rose and fell, their technological debris might still orbit their dead stars, waiting to be spotted. The hunt for biosignatures isn't just about finding life. It's about rewriting the timeline of existence itself. Every flicker of an anomalous gas, every unexplained chemical ratio, could be a clue pointing to a universe that's always been alive, in ways and places we're only beginning to imagine. And if we find even one definitive trace, it won't just answer the question of how early life appeared. It will force us to ask why it ever took so long to find us. Quantum fluctuations are the universe's smallest whispers with the biggest consequences. In the seething chaos of the early cosmos, these subatomic trembles, tiny, unpredictable shifts in energy, were the seeds of everything we see today. Without them, galaxies wouldn't clump together, stars wouldn't ignite, but here's the wild part. These same fluctuations might have done more than shape the cosmos. They could have nudged the universe toward life far earlier than we ever imagined. Picture the primordial universe, a place where particles flickered in and out of existence in fractions of a second. On the quantum scale, empty space isn't empty, it's a frothing sea of potential, where energy burrows itself into fleeting particles before vanishing again. Normally, these fluctuations cancel each other out, leaving no trace. But in the early universe's extreme densities, some of them got frozen into reality, amplified by the rapid expansion of space itself. Those tiny knots of extra density became the gravitational anchors for galaxies, stars, and planets. Now take that idea one step further. If quantum fluctuations sculpted the universe's structure, they might have also fine-tuned the environments where life could emerge. Imagine a region where one of these random fluctuations concentrated organic molecules slightly more densely, or where a pocket of space cooled just a fraction faster, allowing water to pool. In a universe where everything hung in the balance, these microscopic variations could have been the difference between a sterile void and a cradle for biology. There's even a provocative theory that quantum effects could have directly influenced life's chemistry. Enzymes, the molecular machines that drive biological reactions, rely on a strange trick called quantum tunneling, where particles seemingly teleport through barriers they shouldn't be able to cross. This isn't just a quirk of earthly life. It might be a universal shortcut, a way for chemistry to work faster and more efficiently in the harsh conditions of the early cosmos. If quantum biology is fundamental, then life might not have needed perfect conditions, just the right quantum coincidence. But the real surprise is how delicate this balance could have been. Alter a quantum fluctuation by an unimaginably tiny amount, and entire chains of cosmic events shift. A slightly denser patch might collapse into a star too quickly, sterilizing nearby planets with radiation. A slightly emptier one might never form planets at all. The fact that we exist might hinge on a series of quantum accidents, a cosmic lottery where life won the jackpot against impossible odds. And here's the kicker: we might be able to test this. By mapping the universe's oldest light, the cosmic microwave background, scientists can trace the imprint of those primordial quantum ripples. If certain patterns align with the distribution of early galaxies or the chemistry of ancient exoplanets, it could hint at a universe where life wasn't just lucky, but inevitable. Quantum mechanics isn't just the physics of the small. It might be the hidden architect of life itself, weaving complexity into the fabric of reality from the very first moments. The Anthropic Principle turns the universe into a cosmic mirror, one that reflects back an unsettling question. Are the laws of physics just lucky for life, or is there something deeper at play? If life could emerge in the universe's chaotic infancy, it doesn't just hint at resilience, it suggests the cosmos might be wired for biology from the ground up. Think of it like walking into a library and finding every book perfectly arranged for your taste. Coincidence, or was the library built with you in mind? Take the fine-tuning of fundamental constants, the strength of gravity, the charge of an electron, the nuclear forces binding atoms. Tweak any of these by a hair, and stars wouldn't ignite, molecules wouldn't form, and life as we know it would be impossible. Scientists call this the Goldilocks zone of physics, a razor-thin range where the universe permits complexity. But if life arose shockingly early, it implies the zone might be wider than we thought, that the recipe for biology works even in extreme, untested kitchens. Here's where it gets provocative. Some physicists argue that if life can exist in a universe, it must because observers like us are the only ones around to notice. It's like a cosmic version of survivorship bias. We're here to ponder these questions precisely because the laws allowed us to exist. But early life throws a wrench in that logic. If biology flourished when the universe was a volatile toddler, it wasn't just clinging to ideal conditions, it was thriving in scenarios we'd written off as barren. That doesn't just expand life's potential playground, it suggests the universe might be optimized for it. Yet there's a counter-argument lurking in the shadows. What if we're seeing the universe's one winning lottery ticket? Imagine rolling a trillion-sided die and landing on life by sheer chance. Statistically, it's improbable, but in an infinite multiverse, every outcome happens somewhere. Our existence might not be destiny, just a random draw, but here's the catch: the earlier life appears, the less time it has to rely on lucky accidents. If life emerged in 500 million years rather than 5, the odds of it being a fluke shrink dramatically. The Anthropic Principle doesn't just challenge our place in the cosmos, it reframes the search for life altogether. If the universe is hardwired for biology, then life isn't a rare spark in the dark. It's a flame waiting to catch wherever the conditions brush against possibility. And if that's true, then the echoes of those first organisms might still be out there, hidden in the light of ancient stars, whispering that we're not the exception to the universe's rules, we're the proof they were written for us all along. The Drake equation has always been a cosmic conversation starter, a way to quantify our loneliness or abundance in the galaxy. But what happens when we plug in the numbers for a younger, wilder universe? Suddenly, the math gets explosive. Take star formation rates. In today's Milky Way, new stars are born at a leisurely pace, maybe a few per year, but rewind to the universe's first billion years, and galaxies were churning out stars like factories with rates hundreds of times higher. More stars meant more planets, more cosmic real estate where life could take root. And with heavier elements still rare, many of those worlds would have been hydrogen-rich, a potential boon for exotic life forms we're only beginning to imagine. Then there's the fraction of stars with planets. Modern telescopes reveal nearly every star hosts at least one world, but in the early universe, planetary systems might have been even more common. Disks of gas and dust around young stars were thicker, richer in raw materials, and more prone to clumping into planets. Some models suggest protoplanetary disks in that era could have formed super-Earths or gas giants in just 1 million years, a blink compared to our solar system's formation timeline. Faster planet birth means more chances for life to get an early foothold. But the real game changer is the probability of life's emergence itself. On Earth, life appeared almost as soon as the planet cooled. If that's not a fluke, if biology sparks readily given the right ingredients, then early planets bathed in organic molecules from dying stars might have been life's playgrounds. The equation's most uncertain variable, the average lifespan of civilizations, gets even murkier. Would early civilizations have lasted longer, benefiting from billions of extra years to evolve? Or would they have been more vulnerable, cut short by gamma-ray bursts or unstable young stars? Here's the kicker. The Drake equation assumes life needs time to evolve intelligence. But what if it doesn't? Single-celled organisms dominated Earth for 3 billion years before multicellular life emerged. Yet in the lab, scientists have watched simple cells evolve complex behaviors in just months. In a universe where conditions were more extreme but also more energetic, evolution might have worked at warp speed. Microbial mats in boiling vents, organisms thriving in acidic clouds, these aren't just survivors. They're proof that life can adapt fast when pushed. The equation isn't broken, it's just too Earth-centric. By tweaking its parameters for the early cosmos, we're not just solving for aliens. We're confronting a radical idea that life might not be the universe's late bloomer, but its firstborn child. And if that's true, then the silence we hear today isn't emptiness. It's the echo of a story that began long before we were here to listen. Primordial black holes are the universe's shadowy wildcards, objects so strange, so densely packed with mystery, they might rewrite the rules of cosmic history. Unlike the black holes we know today, born from collapsing stars, these ancient anomalies could have formed in the first chaotic seconds after the Big Bang, when the universe was a seething cauldron of energy and pressure. Imagine tiny knots of space-time, some no heavier than an asteroid, others as massive as a star, condensing out of the newborn cosmos like droplets in a fog. Their existence is still theoretical, but if they're real, their influence on the early universe, and possibly even life itself, could be profound. Start with their sheer strangeness. A primordial black hole the size of a grapefruit would weigh as much as Earth. Its gravity so intense it could bend light into a trap. But here's the twist: unlike their stellar counterparts, these relics wouldn't just sit there. They'd dart through space like cosmic ghosts, passing through galaxies, stars, even planets without a trace unless, of course, they got close enough to interact. And that's where things get interesting. Some theories suggest these black holes could have acted as gravitational anchors in the early universe, pulling clouds of gas together to jumpstart the first stars and galaxies. Without them, the cosmos might have taken far longer to light up, but their potential role in life's story is even more mind-bending. Picture a primordial black hole drifting into a young planetary system. Too small to swallow worlds whole, it might instead settle into orbit around a star, its faint gravitational tug stirring the pot of planetary formation. Or consider this: as these black holes slowly evaporate over trillions of years, a process predicted by Stephen Hawking, they release energy. Not much, but in the cold depths of space, even a trickle of heat could make a difference. Microbes on a frozen moon might cluster around a black hole's faint glow, using its radiation as a substitute for sunlight. It's a wild idea, but life on Earth has proven resourceful with far less. Then there's the darker scenario. A passing primordial black hole could wreak havoc, perturbing orbits or triggering cataclysmic collisions. If early civilizations did arise, these unseen wanderers might have been their doom, silent, untraceable destroyers lurking in the cosmic dark. Or perhaps they were the ultimate recyclers, their gravity-shredding planets and comets, scattering life's ingredients across star systems in a form of panspermia more violent than we've ever imagined. The truth is, we don't know. Primordial black holes remain one of cosmology's great what-ifs, but their very possibility forces us to rethink life's potential playgrounds. If they exist, the early universe wasn't just a place of stars and planets. It was a labyrinth of invisible forces where life might have danced in the shadows of objects we're only beginning to dream of. And if we ever find proof of these ancient phantoms, it won't just fill a gap in our physics textbooks. It could reveal a universe where life didn't just emerge in spite of the chaos, but because of it. The Great Filter hypothesis isn't just a theory, it's a cosmic detective story, one where we're piecing together whether the universe is littered with the remains of civilizations that never made it, or if life is simply so improbable that we're the only ones to beat the odds. If life really did emerge in the universe's first few 100 million years, that changes everything about where we think this filter might be hiding. Because if biology sparked that early, only to vanish without a trace, it suggests something out there is ruthlessly efficient at snuffing out life before it can spread. Picture the early universe as a minefield. Gamma-ray bursts, rampant radiation, unstable stars. Any one of these could have sterilized fledgling life before it had a chance to evolve beyond single-celled organisms. But here's the unsettling part. If the filter is behind us, if most life gets wiped out by these ancient cosmic traps, that's actually good news for humanity. It would mean we've already survived the universe's deadliest gauntlet, and the path to the stars might be clear. The alternative is far darker. If the filter isn't in the past but in our future, that implies some unavoidable catastrophe awaits all advanced civilizations. Maybe it's self-destruction, nuclear war, runaway AI, or ecological collapse. Or perhaps it's something we haven't even considered yet, a universal bottleneck that every intelligent species hits, with none surviving to tell the tale. The scariest version of this idea, the silence of the cosmos, isn't because life is rare. It's because something always stops it from lasting. But there's a third possibility, one that's both humbling and exhilarating. What if the Great Filter isn't a single event, but a series of them? Life might have to leap not just one hurdle, but dozens, each more improbable than the last. The rise of multicellular organisms, the evolution of intelligence, the avoidance of technological suicide, each step a roll of the cosmic dice. If that's true, then the universe isn't empty because life can't start. It's empty because staying alive long enough to matter is the hardest game of all. So where does that leave us? If life could arise in the universe's violent infancy, only to disappear, it suggests the filter might be less about biology and more about opportunity. The early cosmos was a place of extremes, brilliant but brief stars, planets bathed in deadly radiation, elements still unevenly scattered. Maybe life did ignite over and over, only to burn out when its host star died too soon or its world was stripped bare by cosmic winds. The filter, then, isn't just about surviving. It's about finding a stage stable enough to perform on before the lights go out. And that's the haunting beauty of this idea. The Great Filter forces us to confront not just the fragility of life, but the fragility of time. A civilization that rises too early might lack the resources to endure. One that rises too late might find the universe already slipping into cold, eternal night. We're left wondering if we're Goldilocks, not just in our place, but in our moment. And if that's true, then the greatest filter of all might not be a catastrophe. It might simply be the ticking clock of the cosmos itself. The next decade of astronomy won't just push boundaries, it might shatter them. With instruments like the James Webb Space Telescope already rewriting the rules of cosmic observation, and the extremely large telescope poised to join the hunt, we're on the verge of glimpsing the universe's first life-friendly environments with unprecedented clarity. These aren't just upgrades to existing technology, they're quantum leaps capable of dissecting the atmospheres of planets so distant, their light has traveled for over 13 billion years to reach us. Take Webb's infrared vision, a game-changer for studying the early cosmos. While optical telescopes struggle with the redshift of ancient starlight, Webb sees right through the haze, capturing detailed spectra of exoplanet atmospheres from epochs when the universe was less than 1 billion years old. Imagine spotting methane, oxygen, or even chlorophyll-like pigments in the light of a world orbiting one of the first stars. These wouldn't just be signs of life, they'd be time capsules, preserving the chemistry of organisms that thrived when galaxies were still taking shape. Then there's the extremely large telescope, with its 39-meter mirror, a colossal eye that will hunt for biosignatures with staggering precision. While Webb excels at peering into the distant past, the ELT will focus on nearby exoplanets in unprecedented detail, refining our understanding of how life might arise under extreme conditions. Together, these instruments form a one-two punch. Webb identifies potential life-bearing worlds in the ancient universe, while the ELT deciphers their mechanics, revealing whether their chemistry could sustain biology. But the real revolution lies in what we aren't expecting. These telescopes might stumble upon anomalies, atmospheric gases in ratios that defy geology, or seasonal changes that hint at alien photosynthesis. Or perhaps they'll find nothing at all, forcing us to confront the eerie possibility that life, even in the universe's youth, was rarer than we dreamed. Either outcome would reshape astrobiology. A detection would prove life is a cosmic imperative, while silence might hint that Earth's story is even more extraordinary than we thought. The stakes couldn't be higher. If life's ingredients were present in the universe's first chapters, these missions could capture the opening lines of a story written billions of years before Earth existed. And if they find nothing, that too would be a revelation, a sign that life's spark, for all its potential, might need more than just the right ingredients. It might need a universe that's patient, stable, and kind, a cosmic stage where the play can run long enough for biology to take its final bow. Cosmic dust might seem like nothing more than interstellar clutter, a tiny flecks of carbon and silicate drifting through the void. But zoom in closer, and you'll discover these microscopic particles are cosmic safe houses, shielding the delicate chemistry of life from the universe's relentless fury. Picture a dust grain no wider than a virus, its surface pitted and porous, floating in the frigid darkness between stars. To the naked eye, it's insignificant. To a fragile organic molecule, it's a fortress. Here's how it works. Space is flooded with ultraviolet radiation, a lethal barrage that can rip apart complex molecules in seconds. But when these molecules stick to dust grains, they're suddenly sheltered. The dust absorbs the radiation's energy like a sponge, dissipating it harmlessly while the molecules clinging to its surface remain intact. In the cold, quiet depths of molecular clouds, these protected compounds can link up, forming chains of sugars, amino acids, even the precursors to RNA. It's like chemistry happening inside a bunker, safe from the cosmic war raging outside. And in the early universe, this shielding would have been even more critical. With young stars pumping out torrents of ultraviolet light and supernova blasting entire regions with X-rays, dust grains might have been the only places where life's ingredients could survive long enough to mix and evolve. Some theories suggest these grains didn't just protect molecules, they actively helped them grow. Their irregular surfaces could have acted like tiny laboratories, channeling energy from starlight or cosmic rays to drive chemical reactions. Imagine a speck of dust covered in ice, its surface crackling with the formation of formaldehyde or methanol, each reaction nudging the universe closer to biology. But dust's heroics don't stop there. When stars and planets form, they're born from collapsing clouds of gas and dust. Those same organic-laden grains get swept up in the process, delivering their molecular cargo directly to newborn worlds. Comets and asteroids, often called the delivery trucks of life's ingredients, are just clumps of this dust in disguise. So when a young planet like Earth finally cools enough for water to pool, It's not starting from scratch, it's inheriting a pre-made toolkit of life's building blocks, courtesy of cosmic dust. The irony is delicious. We think of dust as something to wipe away, a nuisance, but without it, the universe might have remained sterile, its most promising molecules obliterated before they could take their first steps toward complexity. Dust isn't just a bystander in the story of life, it's the quiet guardian that made the plot possible. And if we ever find life elsewhere in the cosmos, we might owe its existence to these unassuming specks, the unsung architects of biology's first draft. Earth's story is a cosmic speech on a blink of geological time between a molten wasteland and a living, breathing world. The oldest confirmed fossils, those microscopic stromatolites from Western Australia, date back 3.4 billion years. But chemical traces in even older rocks hint that life might have been churning away just 400 million years after Earth formed. That's shockingly fast. Imagine a planet cooling from its violent birth, its oceans still steaming, its atmosphere thick with volcanic gases, and yet, somehow, chemistry crossed the threshold into biology almost as soon as the stage was set. This lightning-fast emergence suggests something profound. Life isn't a fussy, high-maintenance phenomenon. Given the right ingredients and a remotely stable environment, it seems to grab the first opportunity it gets. Earth's early conditions were far from gentle, constant asteroid bombardment. Ultraviolet radiation pouring through a thin atmosphere, temperatures swinging wildly. If life could take root here amid that chaos, why not on other worlds bathed in similar extremes? The universe doesn't wait for perfect conditions, it works with what it has. Now scale that up. The elements life needed, carbon, oxygen, nitrogen, weren't unique to Earth. They were forged in stars and scattered across the cosmos by supernova billions of years before our planet existed. If Earth's chemistry could jumpstart biology so quickly, why couldn't the same happen on a planet orbiting one of the universe's first stars? A world with shallow seas warmed by geothermal vents, or a tidally locked moon huddled close to a dim red dwarf, its night side sheltered from lethal radiation. The ingredients were universal, the timeline perhaps far more flexible than we thought. But here's the twist. Earth's early life didn't just survive, it thrived, diversifying into countless forms despite the planet's violent mood swings. That resilience is the real clue. Life isn't a delicate flame snuffed out by the slightest breeze. It's a wildfire spreading wherever it finds the barest foothold. And if that's true, then the silence of the cosmos isn't proof that life is rare. It might just mean we've been looking in the wrong places or the wrong times. The universe's first life could have risen, flourished, and vanished billions of years before Earth's sun even flickered to life, leaving behind only chemical ghosts in long-dead atmospheres. The lesson isn't just about life's tenacity, it's about opportunity. Earth didn't win some cosmic lottery, it simply showed up to a game that might have been playing for eons. And if we're ever going to find our cosmic kin, we might need to stop searching for reflections of our present and start listening for echoes of the universe's distant biological dawn. The rare Earth hypothesis throws a cosmic bucket of cold water on our most optimistic dreams of a universe teeming with life. While the idea of biology igniting in the universe's chaotic dawn is thrilling, this counterargument forces us to confront an unsettling possibility, that even if simple life arose early, the leap to complexity might be a near impossible fluke. Think of it like a million monkeys banging on typewriters. Sure, they might eventually tap out a few coherent words, but producing Shakespeare requires more than random chance. It demands a perfect storm of stability, resources, and time, conditions that might be vanishingly rare, even in a young universe bursting with potential. Take Earth's own story. For 3 billion years, life here was content with single-celled simplicity. The jump to multicellular organisms didn't happen until a dizzying array of factors aligned: oxygen levels rising, predators emerging, genetic mutations stacking like winning lottery tickets. And even then, it nearly didn't happen. If a single asteroid had veered off course or a volcanic eruption tipped the climate differently, we might still be a planet of microbes. Now scale that fragility across the cosmos. Early planets, bathed in radiation and orbiting unstable stars, might have been incubators for life's first sparks, but pressure cookers where complexity could never take root. The hypothesis hinges on galactic real estate. Not all corners of the universe are created equal. To foster advanced life, a planet needs more than just water and organic molecules. It needs a stable star with a long lifespan, a magnetic field to deflect deadly radiation, plate tectonics to recycle nutrients, a massive moon to stabilize its tilt. The list goes on. In the early universe, these luxuries were scarce. Stars burned fast and died young. Planetary systems were jostled by gravitational chaos, and heavy elements necessary for robust biochemistry were still concentrated in isolated pockets. Life might have flickered everywhere, only to snuff out when its host star flared or its world froze over. Yet the rare Earth hypothesis isn't just about bad luck, it's about timing. Even if a few planets stumbled into the right conditions, the universe's early epochs might have been too volatile for life to gain a foothold. Imagine a civilization rising on a world bathed in the glow of one of the first stars, only for a nearby gamma ray burst to sterilize their planet overnight. Or picture a promising biosphere torn apart by gravitational tides as its star drifted too close to a black hole. The early cosmos wasn't just a nursery, it was a gauntlet, and survival might have required a near-miraculous run of cosmic good fortune. But here's the twist: rarity doesn't mean impossibility. Even if the odds are stacked against complex life, in a universe with trillions of galaxies, the improbable becomes inevitable. The rare Earth hypothesis doesn't erase the possibility of early life, it just reframes it. Those first organisms might have been cosmic pioneers, blazing a trail that few could follow. And if that's true, then finding their fossils, whether in ancient Martian rocks or the atmospheres of distant exoplanets, wouldn't just answer whether life existed early. It would reveal whether the universe is a place of boundless creativity or a stage where life gets only the rarest of encores. The multiverse isn't just a sci-fi trope, it's a serious scientific possibility that could rewrite the rules for life's origins. Imagine a cosmic tapestry where countless universes exist alongside ours, each with its own unique physics. Some might have stronger gravity, making stars burn out in a flash. Others could have weaker nuclear forces, preventing atoms from forming at all. But hidden among these infinite variations, there might be universes where the conditions for life aren't just possible, they're inevitable, with biology sparking into existence even faster and more frequently than in our own. Take the fine-tuning problem. Our universe's constants, the strength of gravity, the charge of an electron, are uncannily perfect for life. Tweak them slightly, and stars wouldn't ignite or molecules wouldn't bond. But in a multiverse, that fine-tuning isn't a miracle, it's a statistical certainty. Among trillions of universes, a handful will always hit the jackpot. And some of those lucky universes might have parameters that make life easier to emerge. Picture a cosmos where dark matter interacts just enough to accelerate galaxy formation, where cosmic radiation is gentler, or where organic molecules assemble at lower temperatures. In those realms, life might not need billions of years of cosmic evolution. It could flourish in the universe's first breaths. Here's where it gets wild. If life did arise in a multiverse sibling, its story could be radically different from ours. A universe with stronger electromagnetic forces might see charged molecules forming more readily, supercharging early biochemistry. One with faster expanding space could have stars spread farther apart, reducing deadly gamma-ray bursts and giving fragile organisms a safer environment to evolve. Even the concept of early changes when physics itself is fluid. Time might flow differently, with billions of years compressed into moments or stretched into eons. But the real kicker, we might never know. These alternate universes could be forever beyond our reach, their light fading into unreachable dimensions. Yet their existence hints at something profound. If life can thrive in even one of these exotic realms, then our universe's timeline, where life took nearly 10 billion years to emerge, might not be the rule. It could be the exception. The multiverse doesn't just expand the playing field for life, it shatters the idea that there's only one way or one time for biology to begin. And that leaves us with a humbling thought. If we ever find evidence of life in our universe's ancient past, it might not just hint at our own origins. It could be a glimpse into a broader cosmic truth that life isn't bound by a single set of rules, but is a phenomenon as varied and relentless as the universes themselves. Finding evidence of life from the universe's infancy wouldn't just rewrite textbooks, it would force humanity to confront questions we've never had to ask before. Imagine the moment scientists confirm a biosignature on a planet that existed 12 billion years ago. The euphoria of discovery would quickly give way to a deeper reckoning. How do we handle knowledge that challenges the very framework of our existence? This isn't just about science, it's about stewardship. We'd be holding proof that life isn't a local phenomenon, but a cosmic inevitability, and with that comes responsibility. First, consider the philosophical earthquake. Religions and worldviews built on Earth uniqueness would face profound questions. If life flourished before our solar system even formed, what does that mean for concepts like divine creation or humanity's special place in the cosmos? History shows us how seismic shifts in understanding, like Copernicus displacing Earth from the universe's center, can ripple through societies, sometimes violently. The discovery of ancient extraterrestrial life wouldn't just add a new chapter to science. It could unravel foundational narratives that have guided civilizations for millennia. The ethical response here isn't to dismiss these tensions, but to navigate them with transparency and empathy, ensuring the dissemination of this knowledge doesn't become a tool for division. Then there's the dilemma of interference. If we detect signs of ancient life, especially if it's extinct, should we attempt to study it directly? Sending probes to collect samples from such worlds risks contamination, not just of the alien ecosystem, but of our own. Microbes surviving in the frozen remnants of a long-dead biosphere could pose unknown biological hazards. Conversely, our spacecraft might carry earthly organisms that could falsely appear as native to that world, muddying the evidence. The Outer Space Treaty of 1967 provides some framework prohibiting harmful contamination of celestial bodies, but it was written before we could imagine this scenario. Updating these protocols isn't just bureaucratic, it's a moral imperative to preserve the integrity of both alien life and our own. But the most haunting question is one of legacy. If we find proof that life arose repeatedly in the early universe only to vanish, it forces us to confront our own fragility. Are we looking at a graveyard of civilizations that couldn't survive their own cosmic adolescence? Or are we seeing nature's experiments, biology's first stumbles before it learned to endure? Either way, the discovery would carry a warning. Life may be abundant, but longevity isn't guaranteed. This knowledge should galvanize us to protect our own biosphere with renewed urgency, not out of fear, but from the humbling realization that we might be holding a torch passed to us by countless extinct species across the stars. The search for early life isn't just a technical challenge, it's a mirror. However we choose to respond will reveal more about humanity than about the life we find. Will we approach it with arrogance, treating these discoveries as trophies, or with reverence, recognizing that we're not the universe's first attempt at consciousness, just the latest iteration in a chain stretching back to the dawn of time? The answer will define not just our science but our species. Magnetic fields are the invisible shields of the cosmos, silent, steadfast guardians that can mean the difference between a thriving biosphere and a sterile wasteland. Picture a young planet freshly formed in the chaos of the early universe, its surface bombarded by lethal radiation from a hyperactive sun. Without protection, this world would be cooked alive, its atmosphere stripped away like sand in a hurricane. But wrap that same planet in a robust magnetic field, and suddenly the rules change. Charged particles from stellar winds curve harmlessly around it, deflected by forces unseen. Ultraviolet radiation, while still intense, finds fewer paths to penetrate deep into the atmosphere. It's like comparing a house with no roof to one built inside a fortress. The difference isn't just survival. It's the chance for life to experiment, adapt, and endure. This isn't just theory. Look at Earth's own history. Our magnetic field, generated by the churning of molten iron in the core, has been a silent partner in life's story for billions of years. Without it, solar winds would have eroded our atmosphere long ago, leaving Earth as barren as Mars. Now rewind to the early universe where stars were fiercer, radiation more intense, and cosmic weather far more violent. In that environment, a strong magnetic field wasn't just helpful, it might have been the only lifeline for nascent biology. Planets orbiting volatile young stars could have relied on their magnetic shields to carve out pockets of stability, turning what should have been lethal environments into potential cradles for life. But here's the twist: not all magnetic fields are created equal. The strength and stability of a planet's magnetic shield depend on its core composition and rotation. A world with a sluggish or partially solidified core might generate a weak, flickering field, one that comes and goes like a faulty light bulb. Others, rich in conductive metals and spinning rapidly, could sustain a relentless protective barrier. In the early universe, where heavy elements were still unevenly distributed, this cosmic lottery meant some planets were born winners, while others never stood a chance. A handful of worlds, blessed with the right mix of chemistry and motion, might have been the only places where life could cling to existence amid the chaos. And the surprises don't stop there. Magnetic fields don't just deflect radiation, they shape atmospheres. On Earth, auroras are the visible dance of solar particles spiraling along magnetic field lines, but the process also helps regulate atmospheric chemistry. In the early universe, a strong magnetic field could have prevented the escape of vital hydrogen, keeping a planet's water from being torn apart and lost to space. It might have even directed energy into the upper atmosphere, creating layers of ozone or other protective compounds long before they appeared on Earth. The implications are staggering. A well-shielded planet could have maintained habitable conditions for billions of extra years, giving life time to evolve in environments we'd otherwise write off as hopeless. The lesson here is profound. When we search for life in the cosmos, we often focus on the obvious: the presence of water, the right temperature, the chemistry we know. But magnetic fields are the unsung architects of habitability, the silent variable that might separate a living world from a dead one. And if we ever find evidence of life in the universe's ancient past, we shouldn't just ask if the ingredients were present. We should ask if the planet had a shield, a magnetic embrace strong enough to cradle the first fragile sparks of biology until they could burn on their own. Silicon-based life isn't science fiction, it's a scientific possibility lurking in the periodic table's shadows. While carbon dominates Earth's biology, its cousin silicon shares some startling similarities. Both elements sit in the same group, meaning they can form four bonds, creating the complex molecular chains essential for life. But silicon's chemistry plays by different rules, ones that might have given it an edge in the early universe's extreme environments. Picture a planet scorched by a young star's fury, its surface temperatures soaring past the boiling point of water. Carbon-based molecules would crumble under such heat, but silicon's stronger bonds could hold firm, forging stable structures where carbon would fail. The early cosmos was a crucible for such experiments. Before heavy elements were evenly distributed, planets might have formed with crusts rich in silicon and scant in carbon. In these alien landscapes, chemistry could have taken a detour, assembling life not from the familiar sugars and proteins we know, but from silicon's answer to hydrocarbons and silica gels. Imagine organisms with crystalline skeletons, their metabolisms fueled by volcanic sulfur or metallic salts instead of oxygen. These wouldn't be delicate, water-dependent creatures, but rugged entities thriving in boiling mudflats or deep beneath a planet's crust, where geothermal heat replaces sunlight as an energy source. Yet silicon's Achilles heel is its reactivity. On Earth, it bonds tightly with oxygen, locking away as sand or rock, but the early universe offered workarounds. In oxygen-poor environments, like the atmospheres of gas giants or the depths of sulfur-rich worlds, silicon could have remained free to form complex molecules. Some scientists even speculate about silicon-oxygen hybrids, silicate-based life forms that incorporate both elements, their biology unfolding at a glacial pace in the cold voids between stars. The implications are profound. If silicon life existed, it might leave traces invisible to our carbon-centric tools. Instead of seeking oxygen or methane in exoplanet atmospheres, we'd need to hunt for exotic gases like silane or silicon tetrafluoride. Their presence wouldn't just hint at alien biology, it could point to a shadow biosphere, one that flourished and vanished before carbon ever got its chance. This isn't just about expanding the definition of life. It's about recognizing the universe's creativity. The same cosmic chaos that birthed galaxies and stars might have sculpted life from elements we've overlooked, in places we've dismissed as barren. And if that's true, then the story of biology isn't written solely in carbon script. It's a library of possibilities waiting in the dust of long-dead worlds. Galactic collisions in the early universe weren't just spectacular light shows, they were cosmic pressure cookers, forging environments where life might have gotten its wildest chances. Picture two massive galaxies, each brimming with primordial gas and dust, hurtling toward one another at unimaginable speeds. When they met, it wasn't a gentle merging. It was a cataclysm of gravitational chaos, shockwaves ripping through interstellar clouds, compressing them until they ignited into frenzied bursts of new stars. These weren't the quiet, steady births we see today. These were stellar fireworks with thousands of stars flaring to life in mere millions of years, bathing their surroundings in intense radiation and torrents of raw energy. Yet amid this destruction, something remarkable could have happened. The same shock waves that tore through gas clouds also concentrated them, creating dense pockets where heavy elements carbon, oxygen, iron clustered together in unprecedented quantities. Planets forming in these turbulent nurseries might have been born with a rich endowment of life's building blocks, their surfaces seeded with organic molecules long before things settled down. Even more intriguing, the gravitational turmoil could have flung some of these worlds into unexpected orbits, pulling them out of deadly radiation zones and into the quieter edges of newly forming solar systems. A planet destined for sterilization might suddenly find itself in a gentler orbit, its chances for life resurrected by the very chaos that should have doomed it. But the real wild card was time. Galactic collisions didn't just create brief surges of star formation, they also accelerated it. Normally, a gas cloud might take hundreds of millions of years to collapse into stars and planets. But in the wake of a collision, that process could be compressed into a fraction of that time. For life, this speed might have been critical. A planet forming in 50 million years instead of 500 could have given biology a head start, capitalizing on the universe's chemical abundance before nearby supernova or wandering black holes shattered the fragile peace. The paradox is striking. We think of galaxy collisions as apocalyptic, and they were for countless worlds. But for a select few, they might have been the ultimate crucible, forging habitability in the unlikeliest of places. Imagine a planet forming in the turbulent disk of a colliding galaxy, its atmosphere enriched by the ashes of dead stars, its oceans fed by comets hurled inward by gravitational tides. It wouldn't be a stable place, not by our standards, but stability isn't always life's friend. Sometimes it's the chaos that stirs the pot, forcing chemistry to try new paths, pushing molecules to assemble in ways they never would in calmer waters. And then there's the aftermath. After the collision's fury passed, the merged galaxy would settle into a new equilibrium, its star-forming frenzy fading. But the planets born in that frenzy, they'd remain, carrying the legacy of that violent beginning. Some might have been sterilized by subsequent supernova or rogue black holes. But others, those flung into just the right orbits or sheltered by thick atmospheres, could have nurtured life long after the cosmic storm had passed. We might never find direct evidence of these ancient survivors, but their existence would rewrite the rules. Life wouldn't need a quiet, peaceful cradle. It could emerge in the universe's most violent neighborhoods, thriving not despite the chaos, but because of it. The lesson here isn't just about resilience. It's about opportunity. Galactic collisions didn't just destroy, they created, concentrated, and catalyzed. In a universe where time and chance are everything, these violent encounters might have been life's unlikely midwives, offering fleeting windows where biology could steal a march on the cosmos. And if that's true, then the search for life's origins isn't just about quiet, stable systems. It's about learning to see the universe's most violent moments not as endings, but as beginnings. The universe guards its oldest secrets fiercely. For all our telescopes and supercomputers, the first billion years remain a blur, a cosmic dark age where light is stretched beyond recognition and matter moves to rhythms we can only guess at. We've reconstructed the broad strokes, the first stars flickering on, galaxies assembling like beads on a spider's web. But the details, the ones that could tell us whether life had a shot in that primordial chaos, those are still written in a language we're struggling to decode. Take reionization, that critical epoch when ultraviolet light tore through the universe's hydrogen fog. We know it happened, but the timeline is maddeningly vague. Did it unfold smoothly, giving early planets a fighting chance to develop protective atmospheres? Or was it a series of violent bursts, sterilizing entire regions of space at random? The difference isn't academic. It could mean the window for early life was wide open or slammed shut before biology could take its first breath. Right now, our models are like weather forecasts for a continent we've never seen, educated guesses based on scattered clues. Then there's the puzzle of the first planets themselves. Modern telescopes can spot gas giants orbiting nearby stars, but Earth-sized worlds from 13 billion years ago. Their light is too faint, their signatures drowned out by the glare of their brilliant, short-lived suns. We're left extrapolating from fragments, the chemical leftovers in ancient stars, the rare survivors from that era that drifted into our galactic neighborhood. It's like trying to reconstruct a dinosaur from a single tooth, then guessing what it ate for breakfast. This uncertainty isn't a failure, it's an invitation. Every gap in our knowledge is a playground for bold ideas. Could quantum fluctuations have nudged certain regions toward habitability? Might dark matter's invisible hands have stabilized early solar systems? The wildest theories aren't sci-fi, they're placeholders, waiting for data to either elevate or erase them, and that's where the real excitement lies. The James Webb Space Telescope isn't just filling in blanks, it's revealing that some of our assumptions were wrong all along. Galaxies larger and more mature than expected, black holes growing impossibly fast, each surprise forcing us to redraw the timeline of cosmic evolution. Humility is our most powerful tool in this search. The history of astronomy is littered with overturned certainties, from the geocentric universe to the myth of the unchanging cosmos. Today's facts about early life might be tomorrow's footnotes. That's not discouragement, it's liberation. The universe owes us nothing, least of all simplicity. Its earliest chapters may yet hold forms of life so alien, so divorced from our carbon and water template, that we've been staring right at them without recognition. The irony is delicious. We hunt for life's origins not despite the gaps in our knowledge, but because of them. Every unanswered question is a flickering signal, a whisper that the cosmos still has stories left to tell. And if we listen carefully, with patience, imagination, and just enough audacity, we might hear the faintest echo of all, the sound of biology's first, tentative footsteps across a universe still learning what it means to be alive. The hunt for the universe's first life is about to leap into hyperdrive, not with incremental steps, but with quantum jumps in technology that would have sounded like science fiction just a decade ago. Imagine an AI so finely tuned it can sift through petabytes of telescope data, spotting anomalies in exoplanet atmospheres that human eyes would dismiss as noise. Or a quantum computer simulating primordial chemistry in ways that reveal entirely new pathways for life's origins. These aren't distant dreams, they're tools already taking shape in labs and observatories, poised to crack open cosmic mysteries we've barely begun to articulate. Take machine learning's role in astrobiology. Right now, telescopes like James Webb generate more data in a single observation than a team of scientists could analyze in a lifetime. But AI trained on synthetic biosignatures, hypothetical chemical combinations that might indicate alien life, could flag patterns invisible to traditional methods. Picture an algorithm detecting the faintest traces of a gas produced only by extreme microbial life, or recognizing atmospheric imbalances that suggest a long-dead biosphere. These systems won't just confirm our expectations, they'll surprise us, pointing to life forms so bizarre we haven't even thought to look for them. Then there's quantum computing, a revolution hiding in plain sight. Simulating molecular interactions at the quantum level is impossibly complex for classical computers, especially when dealing with exotic environments like the hydrogen-rich atmospheres of early exoplanets. But quantum machines, with their ability to model multiple states simultaneously, could recreate the precise conditions where silicon-based chemistry or metallic solvents might spawn biology. Suddenly, we're not just guessing whether life could exist in a supercritical fluid on a tidally locked world. We're watching it unfold in a virtual lab, guided by the same quantum rules that govern the real universe. But the real game changers are the next-generation telescopes waiting in the wings, projects like the Habitable Worlds Observatory won't just peer at exoplanets, they'll dissect their light with surgical precision, hunting for biosignatures across thousands of worlds in a single sweep. And with space-based interferometers, we might eventually map the surfaces of Earth-sized planets orbiting stars 100 light-years away, searching for continental outlines or chlorophyll-like pigments in their vegetation. The ultimate prize, a spectral fingerprint of oxygen and methane in the atmosphere of a planet that existed 12 billion years ago, proof that life didn't just emerge early, but thrived when the cosmos was still in its infancy. Yet the most thrilling discoveries might come from tools we haven't even invented yet. Breakthroughs in metamaterials could lead to lenses that bend light in ways that defy conventional optics, revealing details of ancient galaxies currently lost to redshift. Advances in neutrino astronomy might let us detect the faint energy signatures of long-extinct alien civilizations. And who's to say we won't one day decode quantum fluctuations in the cosmic microwave background, uncovering subtle imprints left by technologies far beyond our own. This isn't just about better instruments, it's about rewriting the rules of the search itself. The universe's first life might not announce itself in ways we recognize. It could hide in the quantum states of dark matter or in the fractal patterns of self-replicating crystals deep within icy moons. The tools we're building won't just answer the questions we're asking today. They'll reveal questions we didn't know to ask, tearing open new frontiers in the greatest detective story of all time. How life found a way in the darkness before the stars even learned to shine. From the first blazing stars to the tenacious microbes thriving in Earth's harshest corners, the story of life is far more expansive and far older than we ever imagined. The universe didn't wait for perfect conditions to experiment with biology. It rushed in, testing the boundaries of existence while galaxies were still taking shape. The evidence is mounting. Life could have ignited in the cosmic dawn, clinging to survival in environments we'd consider uninhabitable, rewriting the timeline of our origins. But this revelation isn't just about rewriting textbooks, it's about redefining our cosmic identity. If life emerged when the universe was a turbulent toddler, it means we're not pioneers. We might be latecomers to a party that started billions of years before our sun flickered to life. Imagine civilizations that rose under the glow of the first stars, their stories lost to time, their worlds long since swallowed by the void. Or consider the opposite, that we're among the first, emerging in a universe that's finally calm enough for complex life to endure. Either way, the implications are staggering. Yet for all we've uncovered, the mystery only deepens. Did early life blaze a trail we're unknowingly following, or did it hit dead ends we've yet to encounter? Are we the universe's first successful experiment, or merely its latest iteration? Every discovery, from extremophiles in acidic vents to the chemistry of ancient exoplanets, pulls us closer to answers while revealing new questions. The James Webb Space Telescope's glimpses of early galaxies, the hunt for biosignatures in primordial starlight, even the theoretical possibilities of dark matter's role, each thread weaves a richer tapestry of possibilities. This isn't the end of the search, it's a new beginning. The universe has spent 13 billion years whispering hints about life's origins, and we're finally learning how to listen. So what do you think? If life could arise in the chaos of the cosmos's infancy, does that make us ordinary or extraordinary? Drop your thoughts below and let's keep the conversation going. And if you're as captivated by these cosmic mysteries as we are, hit subscribe. The universe has more secrets to share, and we're just getting started.